slope as rate of change. This slope is the same as the slope that we've been looking at before. So nothing has changed. And that's the good thing about it. So this slope is the same thing as we talked about before, y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. This is the same thing if we look at a function. Y represents a function, y equal to f of x. So this is f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1. And with any slope, we want to make sure that x sub 1 is not the same as x sub 2. So you remember that this was ideally the difference quotient that we talked about. And so this slope here defined as a ratio. Ratio just simply means a fraction of a change in y. We call that change in y, this delta y, with respect to changing of x. So this slope is the same as the change of y all over the change of x. It describes how fast y is changing with respect to x. For a linear function, that is a straight line, the slope may be interpreted as the rate of change of a dependent variable per unit. This dependent variable is f of x. So this dependent variable is f of x, and it depends on an independent variable, which is x, right? So just, I think, fancy terminology just to say the same thing. We're talking about a slope. The average rate of change of a function, just a model. If we look at a person's height as it changes through time, and you see this person when they're 5 years old, and then with respect to when they're 20 years old, the height changes. So what they do and what we do here is, if you take the height at two different intervals, and then if you draw, what they're drawing is this straight line. So what you get is the slope of the secant line. The slope of the secant line is simply given a graph. If I can take 2 points on that graph and draw a straight line, that straight line is called the secant. And then from that, we can get the slope. And the reason why they use the terminology of secant is the goal is to reduce the difference in this change of x. Does that imply also the change of y? Well, that's why we have calculus to investigate that. But this change, we want it to be very small. So that is, instead of going all the way, if we start here at a fixed point, say for example, say you pick this value there and you look for the slope. And then after that, you pick, let's say for example, this point, which corresponds which corresponds to a different slope, but it's a secant as well, that goes here. And then if you pick this point, then we talk about that secant. And if you pick this point, and we try to bring the difference closer and closer over time until we end up looking at the very small neighborhood about that very point there. And once we do that, this secant line tends to now look like a tangent line. Tangent is said to be the line that either crosses or touches a curve at only one point. A secant line crosses a curve or graph at 2 points, but a tangent only at one. So it's at that tangent that later on in life you will spend most of your time dealing with. But as of right now, this average rate of change that they're introducing is the same thing as that difference quotient that we talked about a few days ago. So what is it? This average rate of change of a function? There's no change. It looks the same. This is the change of y with respect to the change of x. It's the change of the y values with respect to the change of the x values. Again, it's the same thing as the slope. Well, this is the formula, so if you have a problem that asks for the average rate of change, this is what we're going to use. All right, let's see. Find the average rate of change of a function. Here, f of x equal to x squared plus 6x, and it goes from x of 1 is 1 to x of 2 is 3. So this average rate of change, and I'll just call it simply the slope. This is f of x of 2 minus f of x of 1 all over x of 2 minus x of 1. So let's come here and find f of x of 1, but x of 1 is said to be 1. So this is f of 1. So I'm going to plug in 1 for x. So this is 1 squared plus 6 times 1. So that just gives us 7. And then f of x of 2, this is f of 3. So this is 3 squared plus 6 times 3. So this is 9 plus here 18. And so this gives us 27. So we plug that in. So this is f of x of 2, but that's f of 3 minus x of 1 is 1. This is divided by x of 2 minus x of 1. That's 3 minus 1. We got f of 3, that's 27, minus f of 1, that gave us 7, all over 2. So this is 20 divided by 2, we just get 10. So again, it's the same as the slope. So we've just learned one formula, that is the formula for the slope. And you recall how powerful that formula is. Yes, recall that the slope is equal to y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. If we multiply both sides by that denominator, this implies that we have m times x sub 2 minus x sub 1 is equal to y sub 2 minus y sub 1. Now, if we let x sub 2 equal to x and y sub 2 equal to y, this implies that we have m times x minus x sub 1 is equal to y minus y sub 1. And we can write it with the y's on the left side. So that is y minus y sub 1 is equal to m times x minus x sub 1. Well, what is that called? The slope point form, exactly. Or the point slope. Okay, so this is the point slope form for the equation of a line. Now notice here that all you've done was just to take one formula, the slope formula, and you derive one of the equations of a line. Now going further, if I take that same formula, and if I evaluate the equation at 0, 4. What's 0, 4 called? 0, 4 is what point? Okay, good. The y-intercept. Yep, very good. Thank you. So this implies that I have y minus b is equal to m times x minus 0. This is y minus b is equal to m times x. Get y by itself, y is equal to mx plus b. What is that? Slope-intercept form. So all you've done was to take one formula, and I even got something better than that. I mean, forget the formula. If you forget that, all I have in my head is just the graph. And so here we look at the rise over the run, this change in y with respect to this change in x. So the slope is this change in y over the change of x. What is my point? Well, it's very clear. I want you to see it. It is possible with mathematics if we understand what's going on. That is, if I understand the picture, if I can see it, because sometimes people, they have trouble seeing formulas or trying to memorize formulas, right? Well, I know I do. I have that problem, which is the reason why I studied mathematics. Because in studying mathematics, I don't remember all this stuff. I just see it right. I see an image in my head. And then from the image, I can deduce everything that I want for this test. Everything. I flunked English. I flunked biology because it was too much stuff to memorize. And none of that stuff related one to another. But with the mathematics, everything is relative. Everything is connected, associated with this, and then you can find the next stage by the inference from the previous. So let's look further. I have some questions for you. All right, help me answer this. If two lines are parallel, describe the relationship between their slopes. Choose the correct answer below. Is it A, if two non-vertical lines are parallel, then the product of the slopes of the two lines is 1. Is that true? Or if two non-vertical lines are parallel, then the sum, we add up the slopes of the two lines and we get 0. Does that sound like something? if two non-vertical lines are parallel, then the product of the slopes, multiply the slopes, and we get, of the two lines, we get -1. Does that sound about right for parallel lines? Okay, say no. Matter of fact, part C goes with what kinds of lines? Part C. Perpendicular. If I have perpendicular lines, if I take those two slopes and multiply them, I get -1. Right, very good. D, if two non-vertical lines are parallel, then they have the same slope. Is that it? All right. Hallelujah. All right. What about this one here? If you know a point on a line and you know the equation of a line perpendicular to this line, explain how to write the line's equation. Let's see. So here they say, first write the point slope form of the line. All right. Substituting the given point for x sub 1 and y sub 1, and the negative reciprocal of the slope of the perpendicular line for m. All right. Let's keep reading. Write the slope-intercept form of the line. This is part B. Y equal to mx plus b. Substituting the given point for x and y and the negative reciprocal of the slopes of the perpendicular line for m. So part B, we're going to rule that one out, right? Because there of how they start, that's incorrect. We want to start with that point slope form, not the slope intercept form. So C, write the point slope form of the line, substituting the given point x sub 1, y sub 1, and the reciprocal of the slope of the perpendicular line for m. What do you think about that one? And then D, write the general form of the line, ax plus bx plus c equals 0, substituting the given point for A and B. So what do you say? Which one is it? A, right? Because if they're perpendicular lines, we talked about their slopes are negative reciprocals. See how part C kind of throws us off? They put the word reciprocal, but we don't have negative, right? So that's the difference there. Right. What is a secant line? If the graph of a function is not a straight line, a line connecting exactly one point on the graph is a secant line. The slope of that line represents the average rate of change. Is that the secant line for part A? Is that the secant? What did we say the secant was? It's based on what? Yes, I'm asking a question. I think I said that before. When you come to my class, we're going to do this, not anything else. If you want to do something else, you can go. You're going to respect me, and I'm going to respect you. All right. What is a secant line? Talked about that when I first came in. Were you listening? I mean, if I'm going to come and do this talking and teaching and you're not listening, then, I mean, what's the whole point? Really, just stay home. I just put videos on the computer and you all just watch it. Yes, ma'am.
A line containing any 2 points on
Thank
the
you.
right
So a secant line is a line that crosses the graph at exactly 2 points. Right? What's the line called that touches or crosses the graph at 1 point? What's that? What's that? Tangent line. Did I not talk about that earlier this morning? So part A would not be the secant if the graph of a function is not a straight line. A line containing any 2 points on the graph is a secant line. The slope of the line represents the constant rate of change between these points. Now, for B, that first sentence is good, but they throw us off in the second sentence. Do you see the word that is of contingency in the second sentence? Okay, let's read them all. If the graph part C of a function is a straight line, a secant line is any line with the same slope. We definitely rule that out because the secant represents, right, the slope of two points. Part D, if the graph of a function is not a straight line, a line containing any 2 points of a graph is a secant line. That's good. The slope of this line represents the average rate. Now watch this. Here they have average. Over here you have, what was I looking at before? Yeah, there they have constant. So the question is, for this idea of the secant line, the slope of this line represents, is it the constant rate of change between these 2 points, or is it the average rate of change between these 2 points? So it's going to be the average, right? Very good. Why is that? Let's, the average, oops. The average rate of change. And then conclusively, this whole idea about this average rate of change defines the fundamental concept in calculus that we call the derivative. What is that? You see here how they begin to make this difference between here, this difference small, and then this change of x small. And in doing so, you end up, you look at these 2 points, look at that slope, right? These 2 points, they start over at D, P and D. You get that straight line, that's a secant. Then you look at P and C. Look at that straight line, you get a secant, the slope of the secant. Then look at P and B. Look at that straight line, get that slope of the secant. Look at P and A. And you keep on, you get this point. And, you know, for calculus, we talk about a dense area. That is, that whatever is being examined are very close. You see, there's a difference with these head shapes. But if it's species, if it's some kind of matter or some cell or DNA, whatever, very, very close. Right? Even in the economic market, you look at these numbers that are very close. And then the closer that you get to each other, you want to make that difference so small that it just appears that we're only focusing on 1 point. If that exists, and if it does, then we call that slope the slope of the tangent, and that gives us the derivative. So that was embedded here. Talk about 1 point. That would be the tangent. Interesting. Any questions there? Good.